see here. We're going? Yes, we're going. Okay, hello. This is Love and Division. I'm going back to my old routine of reviewing books, including stuff that has to do with like science and religion and so forth. So, it's called What is Electron? Edited by Volodymyr Simulik. Volodymyr Simulik. So yeah, it's very, it's very interesting that really we don't know what the electron is. Really, I mean, there's a lot we know about how it behaves, but what exactly is it? And my big question is, why is it? Where's the energy coming from to get it to move in the first place? Where's all that energy coming from? Why is it moving? It's like perpetual motion. I thought we weren't supposed to believe in perpetual motion. Let's see here. Okay, so here's what it says. Okay. The electron is the first elementary particle from both a physical and historical point of view. It is the door to the micro world, to the physics of elementary particles and phenomena. This book is about electron models. The year 1997 marked the centenary of the discovery of the electron as a particle by J.J. Thomson. We have already passed this centenary of Planck's great discovery and the beginning of quantum physics. 2001 marked the 75th anniversary of Schrödinger's equation and the beginning of quantum mechanics, while the year 2003 was the 75th anniversary of Dirac's equation and Dirac's model of the electron. Today, the most widely used theoretical approaches to the physics of the electron and atom are quantum mechanical and field theoretical models based on non-relativistic Schrödinger and relativistic Dirac equations and their probabilistic interpretation. This is the basis of modern quantum field theory. More than 75 years is a long time for physical theory. This theory is the basis for all contemporary calculations of physical phenomena. After 75 years, most physical theories tend to be supplanted by new theories or to be modified. The theory's success as well as its difficulties are not evident to specialists. There is no proof of the uniqueness of the quantum field theory approach to the model of the electron and atom. Are other approaches possible? Quantum field theory may be sufficient to describe the electron, but is it necessary? This theory and its mathematics are very complicated. Can we now propose a simpler construction? Is the electron an extended structure, a compound object made up of subparticles, or is a point-like elementary particle which does not consist of any subparticles? What is the limit of application of modern classical physics based either on the corpuscular wave model in the description of the electron? These and many other questions remain without definitive answers, while experiments on quantum entanglement have given rise to new discussion and debate. New high-precision experimental data, for example, the electric and magnetic dipole moments of the electron, may prove decisive. This book, What is Electron, brings together papers by a number of authors. The main purpose of the book is to present original papers containing new ideas about the electron. What is the electrons? Presents different points of view on the electron, both within the framework of quantum theory and from competing approaches. Original modern models and hypotheses based on new principles are well represented. A comparison of different viewpoints, sometime orthogonal, will aid further development of the physics of the electron. More than 10 different models of the electron are presented here. More than 20 models are discussed briefly. Thus, the book gives a complete picture of contemporary theoretical thinking, traditional and new, about physics and the electron. It must be stressed that the vast majority of the authors do not appeal to quantum field theory, quantum mechanics, or probabilistic Copenhagen interpretation. The approaches adopted by these authors consist in using later mathematics and a later interpretation of the quantum theory. Some of them are sound approaches from the methodological point of view. The editor will not presume to judge the models or the authors. We will not venture to say which model is better and why. The reasons are simple. Readers can reach their own conclusions themselves. Investigation of the electron is by no means finished. My own point of view is presented in my contribution to the book. So what I want my paper to be on an equal footing with other models of the electron presented here. The general analysis of the electron models presented here show that they can be classified as follows: corpuscular and wave, classical quantum, point and extended, structureless, and with structure. The reader can compare and ponder these approaches. I would like to thank the authors for their contributions. It is my hope this volume will prove worthwhile for readers and encourage them to pursue further investigation of the electron models. Volodymyr Simulik. Okay, so all right, page 1. Okay, now the book kind of actually gets more interesting as you go along. Towards the end, there's a lot of beach bum philosophers and stuff like that, which is actually I find very interesting. Jamie Keller, Department of Physics and Quantum Theoretics in Mexico. Space and time are primitive concepts in science, used to describe material objects in relation with other material objects and the evolution of those relations. Mathematical description of those relations result in an observer's geometric frame of reference. To describe the object's behavior, we add one more geometric element, the action attributed to the system of objects. A fundamental concept is that of action carriers. The resulting theory has a deductive character. A comprehensive mass charge, weak charge, spin, magnetic moment theory of the electron is presented from this point of view. The main emphasis is given to the mathematical structures needed and the epistemological issues of the theory. Introduction: Space-time and material objects, mathematical structures. This paper contributes to the construction of a deductive theory of matter starting from first principle and using a single mathematical tool, geometric analysis. We present a comprehensive theory where the analysis is centered in the theory of the electron. It represents a logical continuation of the material presented in the volume, the theory of the electron, a theory of matter from START, and a series of publications. We recast here our fundamental philosophical methodological remark. The theory of the electron developed in the above-mentioned book is based on two main theoretical considerations: the nature of a scientific theory and the elements used to describe nature. The basic purpose of the theory presented here is a description of what can be observed, inferred, related, and predicted within the fundamental limitations of experimental and theoretical science. We do not go beyond these limitations in any sense, nor do we seek to derive fundamental concepts from model structures which might be supposed to be more fundamental. We use three basic elements of physical objects: the phenomena, time, space, and action density. The first element, a one-dimensional manifold time and evolution parameter, a primitive concept universally accepted, is defined by its mathematical properties. The concept of space, frame of reference, is defined using the same considerations through its mathematical description. This requires a three-dimensional manifold in agreement with the anthropological apprehension of nature. The third element of physical nature considered here is given the unfortunate name of density of action and describes the existence of physical objects, assuming action is a one-dimensional manifold joined to the previous four in a geometrical unity. We have refrained from giving this concept a new name because we want to emphasize that we are presenting new conceptual and mathematical structures, Principia Geometrica Physica, In our presentation, an action density field is introduced into space-time frame of reference to describe matter through the properties of this action density distribution. The space-time matter concept is tautological. It is a set of non-separable concepts in nature. Okay, so to get into it, there we go. Let's see here. Epistemological approach. The procedure followed article to define a frame of reference to describe physical objects as a distribution field carrier. A geometric space-time action frame allows a definition of velocities of energy momentum as derivatives, to define field carriers through a set of properties, to describe interaction as the possibility of exchange of energy momentum among the carriers of sets of properties, to find the equations for the interaction fields, to find the sources of the interaction fields, to determine the physical properties of a field of sources in such a form that those fields can be used as carriers, to find the equation for source carriers, to find observation properties of those carriers and identify them as the observed electron and its elementary particle partner, the neutrino. Position and localization, mass, charge, action, space, and time. And so that, this goes in and get into all the math and so. So it sounds to me like what he's doing is he's saying that the electron is kind of derived from this action density. Okay, so let's see here, page 29. I'm going to go through pretty quick. I'm just going to kind of read the abstracts and a little bit of stuff here and there in between. Okay, the electron, this is the next article, the electron in a unified composite model of all fundamental particles and forces. Hidezumi Terazawa, Japan. The electron, one of the most fundamental particles in nature, is described in detail in a unified composite model of all fundamental particles and forces, a candidate for the most fundamental theory in physics. In 1897, J.J. Thomson discovered the electron, one of the most fundamental particles in nature. For more than a century since then, the electron has played a key role in physics as well as science and technology. What is the electron? From the remarkable progress in experimental and theoretical physics in the 20th century, it has become well known that matter consists of atoms, an atom consists of a nucleus and electrons, a nucleus consists of nucleons, protons, and neutrons, and a nucleon consists of quarks. There exist at least 24 fundamental fermions, 6 flavors of leptons, including the electron, and the 18 6 flavors of 3 colors of quarks. In addition, there exist at least 12 gauge bosons, including the photon, the 3 weak bosons, and the color octet of gluons. The quarks have the strong interaction with the gluons, while both the quarks and the leptons have electroweak interactions with a photon for the weak boson. In addition, all these fundamental particles have the gravitational interaction with themselves or through the graviton. Furthermore, it has also become clear that the strong electroweak forces of these fundamental particles fit the standard model in which the strong interactions can be described by quantum chromodynamics. The Yang-Mills gauge theory of color, SU3, while the electroweak interactions can be described by the unified gauge theory of weak isospin, SU2 times hypercharge, U1. The later theory assumes the existence of additional fundamental particles, the Higgs scalars, which should be found in the near future, since there exist so many fundamental particles in nature and so many parameters in the standard model of fundamental forces. It is now hard to believe that all these particles are fundamental, and it is rather natural to assume that the standard model is not the most fundamental theory. But what can be derived as an effective theory at low energies from a more and probably most fundamental theory in physics? In this paper, I shall describe the electron in detail in the unified composite model of all fundamental particles and forces, a candidate for the most fundamental theory in physics. This paper is organized as follows. Section 1, I will introduce the unified composite model of all fundamental particles and forces, in which not only quarks and leptons, including the electron, but also all gauge bosons, including the photon, the weak bosons, and even the graviton, as well as the Higgs scalars, are taken as composite state of subquarks, the more and most fundamental particles. In Section 3, I will explain all properties of electrons, such as the electric charge, the intrinsic spin, angular momentum, and the mass of the unified composite model. Section 4, I will describe all interactions of the electrons, such as the electroweak gravitational interactions as effective interactions at low energies or long distances in the unified composite model. Finally, the last section will be devoted to conclusions and further discussions. Throughout this paper, the natural unit system of h bar equals h over Planck's constant over 2 pi, and the speed of light is 1. Planck's constant is 6.626 times 10 to the minus negative 34 joules. And Planck's constant, of course, c is the speed of light in vacuum. Be understand for simplicity, unless otherwise stated. Also note the electron charge should be understood as units of electric charge, which is 1.602 times 10 to the minus 19 C, unless otherwise stated. Okay, so this one, as you can see, gets very complex very quickly. He goes into the composite nature, but let me see if I can see exactly what he's... okay, composite model of every... Okay, so all the fundamental particles he's saying are composite, but I'm not sure what they're composed of. I don't think he ever really spells out what they're actually composed of. He just gives the mathematical modeling. Okay. I would like to emphasize that the idea of composite models of quarks and leptons, and also gauge bosons as well as Higgs scalars, which was proposed by us theorists in the mid-70s, has just become a subject of experimental relevance in the mid-80s. A century has passed since the discovery of electron, the first elementary particle, and hopefully the compositeness of elementary particles will soon be found. Okay, now I'm going to, I like to put my 2 cents in here and there. Unfortunately, I think that this book was compiled before Thunderbolt's project really came on the scene with the electric universe. I mean, they have a composite model of the electron, which is electron, proton, electron, proton, electron, proton, electron, proton, ad infinitum. Which is really actually kind of interesting, because it really simplifies things immediately. Okay, let's go to prospect for the point electron. Thomas Phipps Jr., Urbana, Illinois, South Busy. Okay, so introduction to relativity of the physical size. Many ingenious models for the electron, perhaps the most stable and fundamental of known particles, have been devised. Some of these discussed elsewhere in this book. Here we shall examine the advantages and prospects of the simplest model of all the mathematical point. It might seem that this could be dismissed at the outset on general philosophical grounds. For example, that a point is infinitely small and therefore, like the infinitely large, operationally indefinable, and hence non-physical. This overlooks the fact that the models are not to be confused with that which is modeled, but are here to be judged by results rather than by inferred resemblance to truth. So I shall not address the imponderable ontology of what is the electron, but only what a point particle model of it might accomplish. As a point of my own philosophy, I claim that this sort of metaphorical approximation to reality is what science of physics at best provides. When it pretends to do more, it trespasses on territories of philosophy, religion, and faith. Which is like, I mean, this is kind of, that's the whole point of the book, sort of, is not to do what he's doing, is to say, let's go beyond mathematical modeling and behavior predictions and get into right, something that's more ontologically satisfying. That's just, but let's see what he has to say. And then on the scale of Newtonian physics, the point particle has done yeoman service as an approximation to everything from planets to bullets, and has given us a Newtonian principle of relativity of physical size. Dirac believed that granularity of atoms brought an end to this Newtonian relativity. He wrote, "So long as big and small are merely relative concepts, it is no help to explain the big in terms of the small. It is therefore necessary to modify classical ideas in such a way as to give an absolute meaning to size. But if we examine not the words Dirac used by the parameters, we discover that his own most widely successful and seminal theory of the electron describes not an extended particle but a mathematical point. Therefore, he himself was the active agent in saving Newtonian relativity on all size scales. It is upon Dirac's success in describing the point electron that we shall build here in seeking consciously to implement a universal principle of relativity of physical size. It will be evidence that such a principle by no means implies the physical proposition that size does not matter. It merely implies the hopeful view that the point particle approximation can be descriptively useful on all size scales, and more cogently that the form or the parameterization of physical descriptive equations is invariant, that is, does not abruptly change at some threshold such as atomic or nuclear. Thus, like another better known relativity principle, it implies mathematical form, preservation, or invariance. Stated in that modest way, it seems to make a good deal of sense, does it not? For if there were an abrupt change in parameterization, would this not have to reflect an unobserved abrupt change in the physics? How else, then, by form preservation, are we to make useful inferences from known physics about the topography of unknown physical descriptive territory? With such questions for clues, we should be able to do a bit of elementary detective work that would not strain Sherlock. Indeed, the implications of size relativity are the only real clue we have to guide us in bettering our pretended knowledge, as embodied in the ludicrously overhyped standard theory of particles on nuclear and subnuclear size scales. Whew, okay. Where are we here? Okay. A rigorized formal correspondence, if size relativity is to be a useful guide in physical exploration, it must apply to the descriptive transition between the Newtonian and atomic descriptive realms, and it must embody rigorous form preservation. That is the first test that the principle must pass before its universality can be sustained. Here, an immediate breakdown of the principle occurs if Dirac is to be believed. Exercising equal parts of optimism and skepticism, let us set aside Dirac's judgment and look closely at the best that can be done in formally aligning classical and quantum mechanics, that is, in setting up a formal correspondence between the two. We need to inquire from preservation under what transformation or group. And once we can see our best chances to improve the existing correspondence between Hamilton-Jacobi mechanics of point particles and the Schrödinger equation, for these two already bear to each other a remarkable formal resemblance. Regrettably, it may be the reader's education has been skimped in regard to the Hamilton-Jacobi formalism of classical canonical mechanics in favor of something more trendy such as string theory. Okay, so that gets pretty deep pretty quick. Let me see if I remember what his point was. I should have kind of wrote down when I was in my notes like what the points were. How did he do this? I forget exactly. Let me see. I'm trying to think about it. It's been a little while since I read this book. Okay, well, let's see. Maybe it's summational. We have seen that point particle mechanics is not dead, and that nuclear dynamics founded on class 3 solutions, which locally violate the Heisenberg postulate, lies easily within the realm. Okay. Of formal descriptive possibility. Such an enhancement of dynamics seems limited on the subatomic scale to a description of electron-positron, a fact that suggests a beta structure hypothesis, that only electrons exist on the finer scale in nature. Our derivation of eigenvalues and of eigenfunctions establishes that stable bound states exist beyond any known on the basis of classical or atomic solutions of our postulated equations of motion for all mechanics. The eigenvalues in question lie within what was termed by Pauli as Zwischenginbrief, the region of real mass energy, but imaginary momentum lying between particle total energies. That fits also with the imaginary value P equals IK squared of the canonical momentum parameter. This furnishes a ready mechanical explanation for nuclear beta processes and encourages further speculation. For instance, that all heavy particles may be aggregates of imaginary momentum electrons in real mass states, electronic states with Zwischengebiet and neutrinos, if found to be one of zero rest mass, may be energy quanta associated with electronic transitions between states of real and imaginary momentum, and distinguished from photons such as zero mass quanta associated with electron transitions between states of real momentum. Zwischengebiet, I don't know exactly how to pronounce that in German, but anyway, that means it's like a vibration motion. That's all that means. It means jittering, like I guess kind of like Brownian motion in his theory, in his model. Okay, so let's go on to spinning electron. Martin Rivas, Theoretical Physics Department, Spain. Okay, classical model for a spinning electron is described. It has been obtained within a kinematical formalism proposed by the author to describe spinning particles. The model satisfies Dirac's equation when quantized. It shows that the charge of the electron is concentrated at a single point, but is never at rest. The charge moves in circles at the speed of light around the center of mass. The center of mass does not coincide with the position of the charge for any classical elementary spinning particle. It is this separation and the motion of the charge that gives rise to the dipole structure of the electron. The spin of the electron contains two contributions. One comes from the motion of the charge, which produces magnetic moment. It is quantized with integer values. The other is related to the angular velocity and is quantized with half-integer values. It is exactly half the first one and points in the opposite direction. When the magnetic moment is written in terms of the total observable spin, one obtains the G equals 2 gyromagnetic ratio. A short-range interaction between two classical spinning electrons is analyzed. It predicts the formation of spin 1 bound state provided some conditions on the relative velocity of the spin orientation are fulfilled, thus suggesting a plausible mechanism for the formation of a Bose-Einstein condensate. The spin of an electron has many years been considered a relativistic and quantum mechanical property, mainly due to the success of Dirac's equations describing a spinning relativistic particle in a quantum context. Nevertheless, in textbooks, the research works, one often reads that the spin is neither a relativistic nor a quantum mechanical property of electron, and that a classical interpretation is also possible. The work of Levi Leblond and subsequent papers by Fuchs and others would show that it is possible to describe spin 1/2 particles in a pure Galilean framework with the same G2 gyromagnetic ratio spin-orbit coupling and Darwin terms as Dirac's equation led to the idea that spin is not strictly a relativistic property of the electron. How am I doing here? What? Good, okay. Although I'm going to do this in parts because it's a long book, and I got, putting my stuff on library. I'm keeping it at around an hour because they'll just cut it off, I think. They're not, library's not ready for bigger videos yet. At any rate, the spin is angular momentum of the electron, and the classical quantum mechanical description of spin is the main subject of the kinematical. A work presents the main results of this formalism, and in particular an analysis of a model of a classical spinning particle whose states are described by Dirac's spinners when quantized. Other contributions are also discussed. Let me see, what page am I on? You're 60. I think I'm going to do this. I'll just keep going, I guess. To understand what classical elementary particle is from the mathematical point of view, we consider the first example of a point particle. It is the simplest geometrical object which we can build any other geometrical body of any size and shape. The point particle is the classical element particle of the Newtonian mechanics and has no spin, yet we know today that spin is one of the intrinsic properties of all known elementary particles. The description of spin is related to the representation of the generators of the rotation group, and we know that it is an intrinsic property since it is related to one of the Casimir operators of the Galilei and Poincare groups. From the Lagrangian point of view, the initial and final state of the point particle is a point on the continuous space-time manifold. In fact, what we fix as boundary conditions for the variational problem are the position at the time and the position at the final time. Recall kinematical variables of any mechanical system, the variables which define the initial and final configuration of the system in this Lagrangian description, the kinematical space, that manifold covered by these variables, the point particle, is a system of 3 degrees of freedom with a 4th dimensional kinematical space. All right, once again, let me see. I don't remember exactly what the point is. I think he's kind of saying that this, you got a point particle that's moving around so much that it simulates extension. I suppose that's. And the big controversy, of course, is that a point charge would explode. You could, no, I'm sorry, it's the other way around. Yeah, the reason they're using point charge, right, is because if it had any extension, they figured it would self-repel and explode. That's why they're having That's why they're having this hard time imagining an electron with any kind of extension in space. Right, because of the self-repulsion. Now, this is another nice thing about the electric universe model, is that you don't have to worry about that. Now, of course, some of the other models in this book try to do that. They try to have, you have an electron with extension at the same time doesn't explode. Okay, let me see if I can get to his summation here. Yeah, right. So he basically, I mean, it's almost kind of like a fan. A fan is spinning. It doesn't take up a whole solid disk, but it acts in time on your finger. If it's spinning fast enough, like it's a solid, that there's no gaps there. I mean, unless you're traveling fast enough, you get through it. I think, anyways. Many experimental facts, this is the conclusion. Many experimental facts of particle physics can be understood from a study of a different kind of relativistic waves. The existence of 3 generations of particles come from the dimension of the physical space, which give 3 kinds of chiral projectors and 3 equivalent wave equations by permutations of the index of right multiplication. The 3 different generations must be treated separately in weak interactions because the gauge groups of the 3 generations are isomorphic but not identical. They do not have the same generators. We know that each generation has 2 leptons, one charged, one of neutral. The neutral lepton, called the neutrino, has no electric charge. Leptons are insensitive to the strong interactions. With weak interactions, parity is maximally violated. We can easily find this result if we suppose that the difference between these objects is due to a different kind of relativistic wave. A neutrino has a wave with a value in its in the even subalgebra and only left. For the charged lepton, we have a left wave, while quarks have a value in the full space-time algebra. The neutrino's wave allows only a mass term, but there is no possible charge. With the left wave, which is not restricted to the even subalgebra, we obtain a wave equation for the charged lepton, and this minimal coupling may be extended to the weak interactions. But this wave produces insensitivity to strong interactions, which is actually only on the missing part of the wave. So, okay, that's kind of interesting. So, because this is the thing, it's really, why is there so much complexity and diversity in, say, the periodic table? Why do these things have such precise behavior? And there's got to be something about, there's got to be something mechanical dictating that all those diverse behaviors. What is the electron? H. Sellhofer, Austria. The hydrogen atom in scalar form. In my youth, I often had talks with Erwin Schrödinger, my teacher at the time, about methods for deriving his famous equation. I tried to simplify the complicated derivation of the time-dependent Schrödinger equations and showed him that one only had to insert the Hamiltonian analogy into the classical equation for light. Then, assuming harmonic solutions, one would obtain the time-dependent Schrödinger equation. Thus, the classical light equation contains Schrödinger's wave mechanics on the basis of its derivation equation. Is simply an equation for light refraction. If light refraction is introduced into a classical light equation, the solutions necessary to describe the light fields. Therefore, it would be most obvious to treat harmonic solutions as the light fields. In this case, Copenhagen interpretation can be dropped. The harmonic solutions of the Coulomb potential produced the hydrogen spectrum. Since the solutions describe standing waves, they substantiate the interpretation. Matter is standing light. Let us visualize this. So that's really interesting, isn't it? This is really cool. Let us visualize this. Any wave train of light has its energy center. Let us imagine two wave trains of light of equal weight, that is, photons which interact with each other. They may, for instance, orbit each other in such a way that each one is reflected by the field of the other. Their energy centers from the Kepler system that generates the hydrogen spectrum. This idea has thus describes, in general, the light model of the hydrogen atom. It does not need an electron. Wow. Using Ehrenfest's center of gravity theorem in this conception, we see that energy centers of the light hydrogen atom move according to Newtonian mechanics. Until his death, Einstein and with him Lorentz, von Laue, de Broglie, Dirac, Landé, Hartmann, and others were of the opinion that Copenhagen interpretation of quantum mechanics is not complete. From that time until recently, only Schrödinger changed his mind. In a commentary to a commemorative publication celebrating his 70th birthday in 1949, Einstein wrote about a quantum mechanics that he could accept. He pointed out that the established part of conventional quantum theory would be found again in the desired new theory, that the new theory most probably had to be of a statistical nature. Then he stated, statistical quantum theory, in case such efforts were successful, would have a status within the framework of the classical mechanics. I am rather firmly convinced that the development of theoretical physics will be such, but the way will be lengthy and difficult. The handicap of Einstein induced some colleagues to look for the missing link between statistical mechanics, Schrödinger's wave mechanics. One researcher, Hoyer of Munster, who 20 years ago in his book, Wellenmechanik auf Statistischer Grundlage, Wave Mechanics on Statistical Basis, put forward a precise derivative of Schrödinger's wave mechanics via statistical mechanics. On the particle path, Hoyer goes directly from Boltzmann to Schrödinger, from Vienna to Vienna. By inserting this statistical theory into the gaping void between Boltzmann and Schrödinger, Hoyer relieved present theoretical physics from the misery of paradoxes and other nuances of the Copenhagen interpretation, which include the indeterminism of microphysics caused by the suspension of the law of causality within its realm, the requirement of a extension of classical logic toward one in which the theorem of excluded third no longer holds, the complementarity of contradicting basic conceptions. The opportunity for general amelioration has not induced our physics community thus far to take advantage of the potential for reform offered by Hoyer. The physicist and philosopher Hoyer remains a voice crying in the wilderness. Hydrogen atom vector form. Okay, so this is pretty this is pretty substantial idea of because it's interesting because the biblical Genesis statement in the beginning God said let there be light. That this idea that everything is made of light somehow is pretty intriguing. Okay, so let's see. Let's go on to the next one. Let me see. Did I miss something? No, I didn't think so. No. Okay. Okay, this is Electron as a system of classical electromagnetic and scalar fields by Volodymyr Simulik of Ukraine. This is the guy that compiled the book. The electron is described as a system of classical electromagnetic and scalar fields. That is, a coupled system of two bosons, photon and massless boson with a spin 0. A mathematical proof of electron structure is given. The main properties of the electron are explained without reference to quantum mechanics or quantum field theory. The slightly generalized classical Maxwell equations are proved to be the equation for the electron. The 19th century conception that matter is electromagnetic in nature is extended here to the idea of more complete bosonic nature of matter. This means that all bosonic fields, not only photonic and electromagnetic, are treated as sources of fermionic fields, which therefore are consequences of bosonic fields. The first elementary particle, the electron, is dealt with here. In order to demonstrate the plausibility of this idea, it must be stressed that the electron is not an elementary object, but has structure. The electron is presented as a system of classical electromagnetic and scalar fields, a standing electromagnetic scalar wave in its stationary states. In other words, the electron is treated as a coupled system of two bosons, photon and massless boson of spin 0. The proof of this assertion is presented below on the basis of the following four arguments. The Maxwell-like equation for the electron, its unitary relationship with Dirac theory, the symmetry principle, derivation of an atomic spectrum from the new equation. Our non-quantum mechanical model of the microworld is a model of the atom based on slightly generalized Maxwell's equations. That is, in the framework of a moderately extended classical microscopic electrodynamics of media. This model is free of probability interpretations and can explain many interatomic phenomena by means of classical physics. Despite the fact that we construct a classical model in building it, we use essentially an analogy with Dirac equation and results achieved on the basis of this equation. It should be also noted that electrodynamics is considered here in terms of field strengths without any reference to vector potentials as initial variables of the theory. The first step is to define the unitary relationship and broad analogy between Dirac's equation and slightly generalized Maxwell equations. Okay. The symmetry principle is the second step. On the basis of this principle, we introduce in the most symmetrical form of generalized Maxwell equation, which can now describe both bosons and fermions because they both have spin 1 and spin 1/2 symmetries. Moreover, the equations are unitary, connected with Dirac's equation. The third step we refer to Selhofer, who suggested the possibility of introducing interaction with an extended field as interaction with a specific media in the Maxwell theory, a new way of introducing interaction into the field equations. Nevertheless, our atom and electron model is essentially different from Selhofer's. We have used another unitary relationship with Dirac's theory. On the basis of these three main ideas, we are able to construct an electrodynamic model of the atom and atomic electron. Interest in the problem, the relationship between Dirac and Maxwell's equations emerged immediately after the creation of quantum mechanics. However, the author of these papers considered the simplest example of the free massless Dirac equation. Interest has grown in recent years thanks to a new result with the investigation of physically meaningful case interaction potential and our own research. In another approach, the quadratic relations between the fermionic and bosonic amplitudes were found and used in our papers, and we here discuss linear relations between fermions and bosonic amplitudes. We have found a relationship between the symmetry properties of the Dirac and Maxwell equations. The complete set of 8 transformations linking these equations is a relationship between the conservation laws for electromagnetic spinor fields, a relationship between Lagrangians for these fields, and the two possibilities for quantization. We have also laid the foundations for classical electrodynamic model of the atom. In recent publications, we added physical interpretation of these mechanical results. Here I present a review of our results together with new interpretation. So basically, he's doing mathematical field trips to explain the mechanics, and needless to say, it's not very easy to understand. Different interpretations of quantum mechanics, Copenhagen, statistical, Feynman's, Everett's translations exist. We are under no illusion that our interpretation should be the only one. Different models of atom have been proposed in this book and elsewhere, but the main point is that classical interpretation without probabilities is now possible. Which is really interesting. I've always had a problem with the probability wave, because it's something that's supposed to have effect on real objects, but but itself doesn't exist. I mean, I don't know how they can get away with that. I can understand that you would have to have the kind of hidden variable that they don't want to allow, but that's ridiculous. They can't just say it's not allowed because they don't know what it would be. It seems to me that 0.0 energy seems random, but I'm one of these people that I have a problem with randomness. That these, one of the best ways always for me to describe these things is with a computer game analogy, that if you have like a computerized soccer, and the player kicks the ball, the ball starts flying through the so-called the simulated air, the simulated ball, and the simulated foot, and there's a simulated inertia. But there's something doing this. There's something doing the simulation. There's an organized way of describing what should take place on the pixels, And so this is kind of the same kind of thing, where there's an organized way of describing what should take place in the voxels, which are your three-dimensional pixel type quantization. So at any rate, I'll stop. This will be part 1. I'll pick up part 2 some other time, because the sun came out and I feel like going outside. So I'll pick this up. I guess one of the reasons I'm doing this, a lot of people don't watch my videos anyway, so I figured I'll do something that nobody will watch. I guess maybe that's my thinking. I'm not sure. There could be a couple people out there that, kind of share my interest in sort of always trying to get to the bottom of the nature of reality. And basically to me it's how did God do these things? And I'm not saying we're going to figure out God or anything. I know somebody will jump on me. They're trying to figure out God, and I'm going to be condemned as a heretic or whatever. No, the whole idea is from the Book of Psalms. You look at God's nature and the way what He created and everything, and you give God glory for the incredible power and sophistication behind this stuff. I'm not suggesting that the scientists were like maybe 150 years ago thinking, oh, we got it all figured out now. It's just a matter of a few little details. They're still as ontologically and epistemologically speaking, the mysteries are still just as wide open in many respects. I mean, what we're talking about, the electron. Well, it's taken for granted that it has perpetual energy. Where does that come from? All right, talk to you next time.